Hello.
Oh, you're here, Serena. Oh, and hi, Doctor. How are you today? Ming. Hi, Serena. I moved you again instead of making you a moderator. um, I wanted to ask you if I'm pronouncing your first name right. Is it Krzysztof? Your unmute button is on the bottom right corner. There's a little microphone symbol, so if you click on there, you can unmute. Yeah.
Yeah,
Perfect.
yes. Hello. I'm unmuted now. Yes,
Yeah.
I can hear you well.
Perfect. And your first name, is it Krzysztof?
Krzysztof.
Krzysztof. Okay.
Yes,
Perfect.
yes, yes.
Yeah, just wanted to make sure that I'm saying it right.
No problem. Yes, this the two letters R and Z are pronounced in Polish as sh,
Sure.
which is a bit tricky for foreigners. Yes.
Thank you. Yeah, my husband's family is originally from Poland, but
Okay.
he was born in Germany, so, and that's where we met. So.
I see. Okay.
But you have been to Hamburg, so you have been working there, so also.
Okay. Yes, I spent in Hamburg 6 years.
A lot of Portuguese live there. I'm
So
originally from Portugal.
you are from Portugal.
Yes, or yeah.
I see.
Yeah. Please feel free. Yeah. Go ahead.
Krzysztof, your audio is very quiet. Is there a way you can move closer to the microphone, or
Is it better now?
a little bit? I'm wondering if there's anything better we can do. I mean, I can hear you. It's just quiet relative to the room.
Okay.
But
I don't
I'm
know.
very excited about this topic. So excited I had to play hooky from work. So don't tell anyone.
I'm excited that you're here. And also meet Frank. He's also helping today with moderating, and yeah. And hi, Jamie.
Hi, Professor Kutak. Thrilled to have you here, and really looking forward to your lecture on the most exciting frontier of knowledge, right? But I'm only an engineer, but always admiring the physics and the most frontier. Yeah, really looking forward to your lecture.
Okay. Thank you very much for the interest. So, can you hear me well? Can you hear me better now?
I can hear. It's a little
Okay.
quiet. I can hear.
Okay. Mm-hmm.
The title itself is so provocative. Chemistry is my background, and we have to build these mental models of what must be going on so we can predict reactions and push electrons around. So it's fascinating to hear perhaps a better picture of what goes on in protons.
Yeah. So it's already 4, right? So when should I start?
I'll introduce you, and then we can go from. Okay.
Okay. Great.
Okay. Yeah. Yeah, we can start. Welcome everyone to the Science Society. It's an honor having today our guest speaker, Dr. Krzysztof Kutak. And let me introduce you and tell you a little bit more about him. He is a professor at the Institute of Nuclear Physics at the Polish Academy of Sciences. And he did his master's at the, I hope I'm saying it right, Jagiellonian University, Krakow, Poland. And then he did his PhD at the University of Hamburg in Germany. And in 2015, his habilitation at Institute of Nuclear Physics, Polish Academy of Science in Krakow. And if you don't know what habilitation means, here in the US, people usually don't have to do it, but in Europe, in some countries, if you want to become a professor, you have an additional step on top of PhD, and that's habilitation. Yeah, he's currently the head of particles of the particle theory department at the Institute of Nuclear Physics and Polish Academy of Science, and he received many honors and awards. One was from the Science and Education for Excellence of Young Polish Scientists, and he also won a scholarship for his PhD at the University of Hamburg. So, and yeah, today we will hear about his very interesting and very groundbreaking research about the inner lives of protons. And yeah, I'm very honored to having you here. Is it okay if Jamie asks you one general question about you as a scientist, and then we go from there?
Yes, that's fine.
Absolutely. Thank you very, very much for coming here, Doctor. I was just wondering, because I was looking at some of your paper, this is fascinating work, but what is it that got you into this? Like, where could you put your origins that led you to here? Did you begin with this in mind, or did you come from a circuitous route, as often scientists do?
Okay, so I got interest in this subject because I was curious about when I was much younger. I was curious about special relativity and about high energies, and then I thought that actually I will become a theoretical particle physicist and work on collider physics. And then I just continue along these lines. So yeah, but I got interest in these topics in theoretical physics and high energy physics already when I was really very young.
So this has always been a passion for you then, from the very beginning. That's interesting.
Yes. This was somehow really since I was even in a primary school. I was just interested in physics. It's somehow unusual, but it started for me very early. I mean, the interest in this kind of problem.
Am I the only one having a hard time hearing the speaker?
He's a little bit quiet, but he's okay.
Maybe you could move closer to your microphone, and I think we can hear you much better. Thank you so much.
Is it better now?
Yeah, we can hear you fine.
Okay.
Everyone else?
Okay.
Everyone? Yep. Okay, one more question for you, actually. When you were actually always focused on this, have you found along your journey, because of course you know more now than you did in primary school, did you find yourself never ceasing to be fascinated by the things you discover along your path?
Well,
Has it stayed interesting? Have you always had more to learn?
well, I mean, I'm not sure if I understand correctly the question, but I'm
Mm, okay.
maybe you could reformulate the question.
Oh, sorry, I was just saying, like, from primary school, when you were always interested in this, do
Yes.
you find yourself still being as amazed as the primary school child that you were? of all the
well,
things you discover?
well, I mean, okay, for this one needs some results to really. Of course, it's not continuously all the time. I mean, like this, like it was. I mean, there are ups and downs, of course. This is so now there are we got some interesting results recently. So I got some new kind of energy to do to new ideas. But let's say when I was working on physics during my PhD, it was not always like that. Sometimes I had to get some complicated results, and it was a bit disappointing that it was not. I mean, it's well, it fluctuates, I would say.
Oh, thank you very much for sharing that. Okay, I'm looking forward to your presentation. Katerina?
Oh yeah, the stage is yours. Thank you for answering those questions.
Okay, so yes. So I would like to talk today about, first of all, thank you for inviting me to give this talk and for the interest in the subject. So I would like to talk about my recent paper with my collaborator from Mexico, Martin Henczynski. He is actually a German physicist, but now is working in Mexico. And yes, and the subject is evidence for the maximally entangled low-X proton in deep inelastic scattering from H1 data. So before going into the really to the main details of our paper, I would like to say some. I would like to introduce you to the theory of quarks and gluons, which is called quantum chromodynamics. The basic objects of quantum chromodynamics are quarks, which and gluons. So here we have two pictures of one of a proton, the other one is of neutron, and they are made of quarks, and the quarks interact between themselves via exchange of gluons. And we know 3 colors of quarks and 8 colors of gluons. And colors here, it is not they are not to be understood as a colors that we know from our, let's say, world. Those are just degrees of freedom which are called in this way. So this is kind of a charge, additional charge of an additional charge which is called color, just to distinguish it from electric charge. So and quarks are charged and gluons are charged. And as I said already, the quantum chromodynamics is a theory which describes you dynamics of interaction of quarks and gluons. So here we have the next slide. On the left, we see two pictures, and one of them is a proton at low energy scale. It is a dilute system. So you see just again 3 quarks interacting with gluons, but on the lower plot, you see the simulation of of uh, of uh, of, of the proton of in of gluons in the proton, which are at much higher energies, and then they form this fluctuating foam. And the system on the top is called dilute, and the other one is dense. On the right, I also made this visualization of how you go from low energy to higher energy. So when you increase energy, let's say if you accelerate the proton, then the energy is transformed into mass according to Einstein's formula, and then you have more and more these spots in the proton, and at some point they form this dense system. And one can introduce an object which is called distribution function, and those functions are on the plot on the bottom of this slide, and they just tell you that, and what is on the x-axis is the some variable which is related to energy, and you see if you go to lower and lower values of this x parameter, then there is this yellow red line. This is the distribution of gluons. It means that that the number of gluons just grows very fast. However, number of the quarks, which are called valence quarks, has the maximum around 10 to minus 2, and then it drops. But then you see also that there is another line. It is denoted as XS. Those are so-called C-quark distributions. And please notice that these two lines are multiplied by 0.05, just so that this distributions fit into the picture. So this distributions just tell you that at certain moment energy scale you have a larger chance of finding gluon. So to some extent this represents this is more, let's say, this distribution allows you to perform some calculations of the possible outcome of experiments at LHC, where you collide protons. So if we go to the next slide, then the next useful concept, which is also used in our paper, is the entropy. So the basic idea behind the slide is the following: that if you look at on this boxes where pictures where I present this blue and red dots, then you see that that the low entropy state is the state where all these blue dots are blue circles are just in a corner, and the red ones are in another corner. And the high entropy state is when they start to mix, and you cannot and even if in more in higher entropy state, then they would just mix more. So the entropy is a useful concept which allow you to distinguish systems where there is order and disorder. And one can think about applying this concept, this entropy concept, to describe or to say something about hadrons, about proton in particular. Another phenomenon is called entanglement. Entanglement basically is a kind of a correlation between various elements of the same system, and basically it tells us that if we have some particles which were interacting, and then we take them far apart, then by analyzing some aspects of one of these particles, we immediately know some aspects of the other particles. For instance, if we have a momentum of particle A measured to be some value, the other one has to be just the some correlated value with the one which we measure. And here is the example on this plot that we have a photon which decays in pair of quark and antiquark. And if we know, and this pair of quark and antiquark, or electron and anti-electron, they form an entangled pair. So we know the spin of the photon, and then if we measure the spin of one of these quark, we immediately know the spin of the other one. So this is the simplest example of entanglement. Okay, so now what is the deep inelastic scattering? So deep inelastic scattering is a process where you have so one should go to the next slide. So where on the top of the slide is deep inelastic scattering. So on this graphics on the right, what do we have here? We have a proton, and this proton is resolved by the photon. So it sees some part of the proton, and it sees the quarks and gluons inside of the proton. But it doesn't have access to the whole of the proton. It just sees a part of it. So the circles, blue circles, just represent decay of the proton after photon interacts with it. And you see that after the interaction, just proton breaks and produces hadrons. And on the left, this is actually a visualization of experiment from DESE in Hamburg, where they performed the deep inelastic scattering experiment. And you see from the left that electron is coming with some energy. On the right, proton is coming. Then electron hits the proton, and it breaks proton. And you see the stream of hadrons, which are denoted as a jet. So those are collimated hadrons. And you see also the recoiled electron. And on the very left, this can be also visualized in terms of something which is called Feynman diagram. So diagrammatic way of visualizing what's happening in the experiment. Go to next slide, please. Why this is relevant? The point is that if we so far, when people were talking about proton, they were just saying that proton is a kind of a sphere which is a object which has zero entropy. It comes from if you take the quantum chromodynamics, perform a lattice simulation of the quarks and gluon fields, you get the object which is called proton, which has this zero entropy. So it is the point is that you don't have direct access to quarks and gluons, and in a lattice QCD simulations, all the final objects that you obtain have to be have to have zero color. So you don't see directly quarks and gluons. And this led people to the conclusion that that proton is a object which doesn't have entropy, which is called a pure state. But on the other hand, if we I shown to you on previous slides this partonic description, this description of proton in terms of quarks and gluons, which you can access in a deep inelastic experiment. And then to predict to get some results from this deep inelastic experiment from the theoretical, one has to introduce this parton density functions. One has to imagine proton as a collection of quarks and gluons which interact between themselves. So then there is a contradiction between this picture of that comes from direct simulations of a computer, that the proton is just a ball which doesn't have which has zero entropy. It is a contradiction with the picture when you which I presented on this previous slides, where if you go to higher and higher energy, you have more and more quarks and gluons inside of a proton. So so then the question. So then Kharzeev and Levin make this proposal that what happens is the following. Indeed, if you look at the whole proton as the whole object, you don't see internal structure. It is a pure state. But then if you perform this deep inelastic scattering, you see the internal structure, and then but only you see the only part of the proton, and you have to yes, okay, so that's enough for the moment. I go to the next slide. So the whole proton is described in terms of object called the proton wave function. And now the key observation is that one can introduce one has two possibilities. First of all, is that you have a not entangled states. It is just a function which describes this unobserved and observed part of the proton. This unobserved is just denoted by blue, while this observed is just you see that it is kind of ellipsa, white ellipsa, and with many partons inside. And then one could have two possibilities. So separable state, where one of this function describes just this blue part, and the other one this resolved, and entangled state, where there is the product is more complicated, and it's not a simple product of two elements. It is just one has the product and also one has some sum. And this part is entangled. It means that by looking at the proton, you in principle are also affected by the other part, to which you don't have in this deep inelastic scattering. You don't have direct access, but it affects you. And the thing that this object, the point is that this object, this part B is not accessible, but one has to take its contribution into account. And then by performing this summation, one gets non-zero entropy. So if we would calculate the entropy of the whole proton, it is by calculating entropy of the whole proton, I mean just by calculating entropy of this density matrix rho AB, which is just denoted by this symbol rho AB. So density matrix is a generalized distribution which tells you about the properties of your system. But if you just neglect, I mean, just sum over some region of the proton, you have another distribution, another density matrix, and this entropy of this density matrix, of this so-called reduced density matrix, has already entropy. So in fact, the statement is that if you look at the basic take home from this slide is that if you look at the whole proton, it has zero entropy. But if you resolve the proton, then you can define some entropy, and you can associate entropy with the proton at given energy scale. So this is something which is actually very revolutionary to introduce the concept of entropy of the proton, because up to now and actually up to now, people were just saying, okay, entropy of proton is zero, and it doesn't even make sense about discussing entropy of proton. Okay, please go to the next slide. So how to really see this in experiment? So the statement is that if you look inside of the proton, you see quarks and gluons, but then proton, after this experiment, just proton breaks into hadrons, and you can measure the produced hadrons. You can just collect them and calculate entropy of this produced hadrons. And the observation is that because of entanglement of this observed region and unobserved region, the entropy of produced hadrons is just the same as entropy of resolved proton. So by measuring by looking inside the proton and then calculating entropy of this distribution functions which parameterize the partons inside of a proton, you can predict the entropy of produced hadrons in the deep inelastic scattering experiment. So now, what it means that the proton is the maximally entangled state. So maximal entanglement, it means that if you perform the experiment if you collide electron with photon, proton breaks down, and then you perform, let's say, this experiment many times, and the statement is that you will never know in the how many hadrons will be produced in each experiment. So let's say if you collide the photon with the proton, you can in experiment number 1 you will produce 3 hadrons. In experiment number 2, 5 hadrons, and so on and so on. So this means that you cannot predict how many hadrons you collide. It means that in principle so this just means maximal entanglement. All probabilities are equal. Everything is possible. Okay, next slide, please. So now I'm on the slide KL formula Monte Carlo and data. So after Kharzeev and Levin wrote the paper, the experimental group at DESY wanted to check their formula. And what they did, they just took parton density, gluon density, because Kharzeev and Levin said that basically the main contribution to this entropy, the whole of the entropy will be just given by gluons. So then they just wrote that entropy equals logarithm of gluons. And this is what experimental group did. They calculated the entropy using some parton density functions, and we see that the continuous lines do not match the experimental data, which is denoted here by these blue dots, red squares, green and red symbols. The next calculation was just by applying some Monte Carlo program, which simulates the whole experiment. And in principle, the agreement is to some extent better. But as it is with Monte Carlo generators, you run it and you are not sure of what really happened. But at least the tendency is not too bad. I mean, the gluon density grows, the entropy grows, so there is some chance. So in the next attempt, so the statement was that in principle the formula is wrong. But what happened here is that the experimental group used these gluon density functions, which are not really consistent with the proposal by Kharzeev and Levin. And so then what they did, they instead said, okay, let's use quark distributions. So and then let's calculate entropy from quarks. But the problem is that they made a mistake in their calculation and got agreement, but this was just accidental agreement. So what we did is the following. We took we just thought, okay, it's not enough to calculate entropy just by using gluon density, by just looking into gluons. One has to take into account both contributions, because quarks and gluons they make proton. So we should calculate entropy of both contributions. Yeah, and furthermore, we decided to use the framework which is consistent with the proposal by Kharzeev-Levin. It is evolution equation, which gives you distributions of quarks and gluons that grow when energy grows. So this is a bit technical, but basically the statement is that we have some formula for quark density and for gluon density. And with this, we described we just took the same data as the experimental collaboration, and we performed the calculation. So the green line is our result, which gets contribution from both quarks and gluons. The red line is just gluons. So we see that with just gluons, it is not enough to describe data. And the blue line is another distribution, another gluon density, quark and gluon density, which is just to see that it doesn't. It's not describing that well the data, because it's based on different evolution equation, not evolution equation in energy. So here are my conclusions. So basically, our result is that we decided to, we realized that one has to combine quarks and gluons, and then we used equation which describes the proper dynamics of quarks and gluons. And furthermore, of course, there are some still open questions. What happens if you go to even higher energies? Whether entropy will grow or whether it will saturate. And actually, the same picture can be, the same discussion can be applied to study another hadrons, like, for instance, neutron or nuclei. Okay, so I'll stop here. Thank you.
Yeah, thank you so much for explaining this so well. When I read the paper and also the news article, I had kind of an idea, but now I understand it much better. Not that I will understand it at the level that I could study this ever. That, you know, I could follow. So thank you so much. It's such a complicated subject, and you explained it so well. So please, everyone, if you have a question, please flash your mic or just go ahead.
Yes, good morning, Katarina and Serena. Thank you, first of all, for hosting another wonderful room, and appreciate you inviting me to be a part of it, because it's particularly special to me to meet Dr. Krzysztof Kutak. Witam, panie profesorze.
Dzień dobry.
Dzień dobry. Greetings from Los Angeles, California. And Katarina was good enough to send me your bio. And so happens I am on my way to Poland, and I just listened to your lecture, and very interesting. And I will have a couple of questions about application of your research, but just to take care of a couple of opportunities, I am flying to Poland this Sunday to participate as a key speaker at the European Union Economic and Science Conference in Katowice. So I'd be happy to follow up our meeting here today with possibility of talking in Poland. I can also invite you to, we are hosting a special party with Baker McKenzie on Monday. So sorry guys, just quickly taking care of some potentially important results of your room. I also I am originally from Poland, as you can hear, but I am a space innovator and leader and space entrepreneur. And what it means is I find economic and social ways of the big scale to further science and economic progress relevant to space. Thus, my question to you will be based in two areas. And yes, by the way, I happened to meet with Madam Vice President Kamala Harris on Monday at the Vandenberg Space Force Base in California. It was a meeting dedicated also partially to science, but focus on a space development, technology, and policy. So quickly, and I am delighted to see you here, because Poland is so abundant in incredible science and scientists and universities. And what we lack is something that Katerina and Serena and other hosts made it possible here, which is giving a visibility to Polish scientists like Dr. Kutak, and I think this is absolutely terrific. My question is as follows. Can you connect in any way focus of your research to application to space in even a faraway way. And two, I just shared with Katerina that as a result of my meeting with Madam Vice President Harris, I am putting together a second proposal that I have already created of California Space Center next to Vandenberg. And by the way, importance of Vandenberg is this is where the science comes to life, because Vandenberg is our premier space rocket launch and space application facility here in California, frequently not remembered by a lot. And I also met with Dr. Armstrong, who is the president of Cal Poly in San Luis Obispo, and we agreed to find the ways to collaborate. So here it is. This is how I could quickly come up with some relevance to your incredible lecture based on my activities in my life. So be very happy to listen, and I will send you a message. And again, Katerina, Serena, thank you for being, as always, incredible facilitators and ambassadors on behalf of science. Uh, I am Lady Rocket, and I am done. Thank you.
Okay, thank you for the question. Well, so the direct application, I think it's rather far, but I don't know. I mean, this is what is for sure interesting about this result is that in principle one could think about a proton as a very complicated quantum computer because which we cannot use now really. But all these efforts to do quantum computations, they are based on some concept from information theory like this quantum logical gates and entropy and all these kind of things. So here we see that proton has some kind of entropy, and all the theory which describes quarks and gluons interactions is based on objects which are called unitary matrices. That's what I can say now. Furthermore, there is okay. It's not a practical, but you see, at some point people discovered that black hole has entropy, and and now still people are amazed by this and working on that. And now we discovered that protons have entropy. So I mean, so 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 maybe there is some relevance for the subject that you are working on, but but I don't know. I mean, there are, most of the cosmic rays are hadrons. So maybe this can be somehow maybe there is some link, but one has to think about it.
Yeah, you inspired me. If I made just application, or I will at least suggest it here, a scientific application. My company, Copernic Space, proszę zobaczyć, Copernic Space się pisze.com, is also using NFTs to finance otherwise difficult to finance projects, fulfilling or removing a financial gap between the science and ability to make it happen. Our NFT is, for example, used to help to provide additional sources of funding for the first private mission to the moon. So, project that we are working on right now is putting, you mentioned computation capabilities, and just a food for thought, and we can take it offline, but we are starting to develop NFTs to finance a project to do crypto mining in space with computers being attached to the satellites. I know it's very far away from what you were talking to us today, but I would be very happy to explore possibility of issuing NFTs to finance far out projects that could involve, for example, results of your science. And this is also what I will be discussing in Katowice. We are very open to support science through financial innovation, which is key to scientists and space. Okay, so thank you. And I just send
Thank
you
you.
my email, and
Okay,
feel free to
great.
connect with me.
Okay, thank you.
Yeah,
Proszę bardzo i życzę powodzenia. Dziękuję.
Dziękuję.
yeah, thank you so much. The yeah, I had the question about now that Lady Rocket mentioned space and you mentioned black holes. Um, this is probably off topic, but wasn't there an idea to use basically the energy of black holes as a propulsion energy source? And is your um, is your evidence here supporting that theory that one day we could use that, or yeah?
Okay, there is some theorem by Penrose, which it's called some Penrose process, but where you could somehow use some energy from black hole to do something useful, but I don't know this in more details. So I cannot give really more insight into this.
Oh yeah, I'm sorry to go off topic. Okay,
No problem.
Abyss, I think I saw you flashing a.
Hi, Dr. Kutak. I joined in the discussion, your presentation phase, much later. Thank you for that, and it's a really inspiring work. In fact, it reminds me of when you talked about um, like protons being computers. There's this sci-fi book that I'm really inspired by. It's called The Three-Body Problem, where
Oh yes,
aliens were
I
able
know
to,
the book.
yeah, were able to etch some kind of computer in a proton. So it did remind me of that. So I do have a couple of questions for you. The first one being that, so you mentioned that protons have, or at least like in your observation, protons appear to have like a zero entropy. I guess like that could be thermodynamic or information entropy. I'm probably missing that part, but do you also expect the same thing with other kind of baryons,
Yes,
especially like
yes.
within? Okay,
Yes, because well, I mean this entanglement entropy in certain limit, one can link it to this information entropy. This is one thing. The other thing is for at higher energies. Uh, well, I mean, if you probe neutron or pion, you just look into the content of these objects like gluons and quarks. So this is universal in some sense. So they also have entropy. So the so this is universal result. It's not only about protons. We studied protons, but at certain uh, energy, the details, whether it's they, they don't matter. This is just general statement.
gotcha. Um, my second question is that I think towards to the last slide, which is I think the appendix, you talked about inelastic scattering. So I come from optics background. So uh, in optics, I guess like the elastic and inelastic scattering are directly related to how much of like a photon is actually carrying the energy, the original energy
Yes,
that's
yes.
after it oscillates a particle. Um, is it fair to kind of say the same thing with other subatomic particles? Of course, like the currency may not be a photon, obviously, because we're talking about gluons uh, and quarks here. So yeah, I'm just interested like what elastic and inelastic scattering is on other subatomic particles.
Yes. Inelastic, deep inelastic here, it means that when you throw with the electron into proton, they exchange a photon, and then this proton breaks into hadrons. It is destroyed. So, but elastic, it means that it just interacts with it, and then sees kind of roughly the proton, but it doesn't break it. It is
I
just
see.
yes, this distinction. In one case, you can completely destroy proton, and you see remnants of the proton and newly produced hadrons. In the other case, it is just you image the proton.
I see.
I,
S- uh,
go ahead.
a quick
Sorry.
follow-up, yeah. So I'm just wondering, like, when you have an elastic scattering, when the subatomic particle kind of breaks, or at least like the particle breaks down to um, other particles, like you just mentioned,
Mm-hmm.
do you see some kind of dip in, or at least like energy transfer? Because like that's typical in elastic
Yes,
scattering and photons. Okay,
yes.
all right. Thank you so much.
You're welcome.
I have a question. So, you mentioned, so you basically predict that, like based on your theory, we cannot predict that when a proton is hit by a photon, um, of what this interaction will turn into, like in what the proton will decay. Is that, did I understand it?
Yes, yes, yes. So one can calculate, uh, yes, for given process, which you basically yes. I mean this to you cannot be. This is basic feature of quantum mechanics, that you can calculate a probability of what can happen, but you will not have the definite answer. I mean, with certain probability, something may happen. This is something that you calculate, but in particular collision, you will not know for for 100% what will be the outcome of the collision. This is this
It,
is this is this is kind of a general. This is known from quantum mechanics, but now explicitly we know that the proton, the structure of the photon, really sticks to this general mm, requirements of quantum mechanics.
that's so
This
interesting
yeah.
because, there's always this big question about if the universe is deterministic or not.
Yes,
I'm not
yes,
sure if
yes,
I'm,
yes,
yes.
yes, yes.
So does your results basically support the
Yes, yes,
non-deterministic?
exactly. I mean, this just says that the proton is a that the internal structure of proton is completely undeterministic.
This is such a big result. That's why I was so interested in having you here. This is, for me, I'm so glad. I was
Thank you for the interest.
because I thought it would be horrible to have a deterministic universe. So I'm so glad you have this result. So, but Frank, you're on mic. So.
Oh yeah. Thanks again, for sharing your precious time with us and educate us on this very deep subject. Um, I do have. Please bear with me because I'm, just sitting in this classroom as a, a student to, for a high, high physics, particle physics lecture. I do have a few naive questions that so to me, I read a little bit before your lecture. I mean, Katerina asked me to, probably help with the. So I read a few things that made connections to your lecture that the pure states, they are so if so they which is verified from you that they should have entropy zero, right? So they but however, if you have part of it, then it's supposed to be mixed. It's actually in mixed state, right? So then
Yes,
the
yes,
entropy would arise, right? So
yes,
that seems to be logical. So your work is essentially verifying the supporting, but I
yes,
think it's
yes,
great that you actually come up with a way of predicting, correcting the previous experiments to say that it's actually even more uniform by counting all the constituents, not just gluon, but also quarks, right? So, um, but my question is on your experiment setup, uh, I read in one of the popular science article explaining your work. There it says using photon, with a high enough energy, so it's short enough to be inelastic into the core of proton. The but your illustration figure on the slides number, I think it's wait, you have the setup where you are shooting. I think the slides number 6, that you're shooting uh, electron. Is that
yes, yes. But electron interacts with the proton via exchange of
virtual
the photon.
photons?
Yes.
Oh, I see. Then, uh, what are the outcomes? Are the gluon and the one you counted all of the
The
outcomes?
outcome is the hadrons. If
The
you look
hadrons,
at
yeah.
the, yes, maybe I have it somewhere. Yes, I have it on slide number 13. If you look at slide number 13, this is let's say diagrammatic picture. So then you see this virtual photon, and then there are kind of springs. Those are gluons, and this lines with arrows. Those are quarks, and they just depict quarks and gluons, which are producing the which after which then transform into hadrons. This is the process is of conversion of gluons and quarks into final state hadrons is due to some features of QCD called confinement. You don't see the color degrees of freedom, you see hadrons. But basically, all these springs, all these lines, they just are final state particles, which are produced after the collision, and they are called they will transform into hadrons.
Okay. So the hadron are the outcomes. The
Yes, yes.
so
Yes,
so
hadrons are
the
the outcomes.
previous the work that you referred to, they somehow, as you said, that they build basically draw the gluon densities. So you think
Yes,
that's incorrect? So are they
this is
talking about the same experiment or not?
yes, this is the same experiment, but then the thing is that they derive, Kharzeev and Levin, they derive the formula based on some uh, on QCD. They derive the formula, which is just gives you entropy as a sum of hadrons. But then they said that that they will just use the gluon density for this for this. If you look at the formula, let me check. Uh, okay, on page 9. On page 9, you have logarithm of n. Logarithm of n, and then this n depends on 1 over x and q. N is the number of partons. So quarks and so the concept was that it should be partons, but then for some reason, but then they derive formula for gluons, and then they claim that gluons is actually really enough, that this should be really dominating and yeah, but we realized, okay, quarks and quarks, but we realized that I mean, gluons are not isolated from quarks. They are strongly interacting with quarks, and 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 then even at high energy regime, the quark contribution can be relevant. So that's why then if you look at slide 14, you see that indeed gluons are relevant. They give something like 80%, but really to match the data, you need also quarks. So we need to describe the whole system of partons, not only gluons.
I see. Just to, I guess understand the whole thing. I probably I have got the very basic wrong. So the small x, I mean the 1 over x. So which one is which end is the high energy?
High energy is the okay. 1 over x, basically it tells this is a certain parameter used in this physics, but I don't. Maybe I okay. I can tell you exactly what is x. X is if you consider proton, right? If you consider proton, then you can picture yourself this partons like quarks and gluon. Okay, no, sorry. If you consider the proton, which is moving very fast, the proton is moving very fast, and these partons, quarks and gluons, are moving with this proton. And the x is the longitudinal momentum component of this partons. So if you have many partons, all these fractions add to the whole momentum of the proton. So they just it is a kind of a parameter which divides the whole proton into quarks and gluons. So if x becomes smaller and smaller, it means that you have more and more quarks and gluons. And then the picture is that if you go to higher and higher energies, then you have more and more quarks and gluons. So in principle, small x corresponds to large energies and large number of partons. So you can talk about either small x or large energy. So this small x is a convenient variable used in equations and in calculating cross sections. But basically, that's the longitudinal momentum component of the quark, which is inside of the proton.
I see. So I guess this is the dense part that you're referring to for the small x. Okay. So you're hopefully, in the future you have a higher energy experiment to explore to make your curve even more data points and even more convincing.
Yes, exactly. There will be actually there are plans for proton lead and lead collisions at Large Hadron Collider, which will probe this dense system. And then there is going to be a new experiment at the United States in Brookhaven National Laboratory, Electron Ion Collider. It's going to be launched in around 2030.
Oh, great. I have a good friend of mine that is their nuclear physicist. So if you come and visit, you should let us know.
So I'm going to be in US actually in July for 4 months.
Oh, here?
BNL.
In Brookhaven? Or?
Yes, in Brookhaven.
Oh,
Brookhaven
wonderful.
National Laboratory, yes.
Oh, we should meet. And because I will for sure, our families are friends, so our kids meet all the time. So yeah, we should meet. That's great.
Oh, yes, thanks.
I think it's a really nice department. So yeah, it's great. Great. Are there any last questions? Because we are a little bit over 1 hour, so I wanted to close at the time we kind of decided on. So if there's any last question, please go ahead. Flash your mic. If not, I want to thank you so much, Professor, that you came here today and shared your knowledge. I hope we'll stay in touch and you come back again with updates of your very groundbreaking and answering the very important big questions of solving how our universe works. So thank you so much. This was a great honor. We really appreciate it.
Thank you very much for inviting me, and yes, I will be glad really to give more talks in the future if I will have interesting results. Sure.
Yeah,
Thank
sure.
you very much.
Thank you very much for your time, Doctor.
Thank you.
And thank you, everyone. Oh, sorry, go ahead. Thank you, everyone in the audience and everyone that asked questions. We really appreciate it. And, follow the club if you like talks like this. And we have later a guest speaker coming talking about lung cancer in smokers, that actually smokers don't have as much lung cancer as people used to expect, and why that is. So, yeah, thank you so much again, Professor, and thank you, everyone. Enjoy the rest of your evening, and bye, everyone.